Hello everyone and welcome back to another video. Today I wanted to make the second installment in my number theory series, and in this video we're going to talk about the division algorithm. This theorem gives us a useful way to express natural numbers that we're going to use often in our future proofs, and it also provides us with an insight into how division on the natural numbers works. Finally, we're going to show how division connects with congruence, which we talked about in the last video, through the concept of the remainder in the division algorithm. So before we jump into the division algorithm, we need to define an axiom that we're going to depend on in our proof. In simplest terms, an axiom is just a statement that's so obviously true that we can accept it as true without proof. We can use an axiom as a starting point when we're developing our proofs. Now, if we wanted to take a more formal approach to number theory, we would start with set theory and the axioms of that, and ultimately define natural numbers, and this axiom would be used in that definition of natural numbers. However, in this context, we're starting off, our starting point is the natural numbers that we're all intuitively familiar with. We all understand how to count, hopefully. So we're going to start with the natural numbers as our starting point, so we can treat this axiom as an obviously true starting point in number theory, or as an axiom in number theory. And this axiom that we're talking about is the well-ordering axiom, as you can probably see up there on the screen right there. So without further ado, let's define what this is and explain what it is. So the well-ordering axiom for natural numbers is this. So we're going to start by we're defining a set. So we're going to let S be any non-empty set of natural numbers. Then, and this is the axiom, S has the smallest element. And this axiom should strike you as obviously true. If you have a set of natural numbers, say like 1, 2, 3, which we're going to talk about, or like any other sort of set, there's some smallest element. There's some order to natural numbers, and one of those numbers in a set of natural numbers is going to be the smallest element just based on that ordering. So this is kind of an axiomatic statement that we can use in all of our proofs about natural numbers. So let us talk about, let's look at some examples to begin with. So for the first example, let's look at just the one we talked about before, S 1, 2, 3. S is 1, 2, 3. So here, obviously, as a smallest element, that smallest element is 1. Next, another set could be this set. They're all going to be natural numbers, 5, 4, 7. And here we have 4. That's another example of a natural number. And then another one could be, let's think about the empty set. Well, there's no elements here, so it doesn't have a smallest element that we can choose. So that's why it's crucial that S has to be a non-empty set of natural numbers, essentially. So now that we have this axiom, how can this be useful in proofs? This seems really obvious. This seems like it might not even be useful. It's so obvious. Well, just to see its usefulness quickly, let's look at a very quick example theorem. For every natural number n, there is a natural number k such that 7k differs from n by less than 7. Okay, let's look at the proof of this. So for the proof, we're going to let n be a natural, and we're going to define a set of naturals. That is, we're going to let S be the set of naturals 7i for where I is a natural and 7i is greater than or equal to n, that number we defined before. Okay, so then what we should first do, we're going to note that S is non-empty. That's important for these types of proofs, to use the well-ordering axiom. Because when I equals n, 7i or 7n is greater than n, basically. 7n is a member of this set because n is a natural and 7n is greater than or equal to n. So by the well-ordering axiom, S has a smallest element. And then we can call this element, we'll say this element is 7j for j, where j is a natural number. So look here, this is what we did. We used that well-ordering axiom, and we're saying that there's some smallest element in that set because S is a set of natural numbers. So because of that, we can pull out that smallest element, which is 7j. We know that it's 7 times some natural number, and it's also the smallest element. So there's no other elements in this set that are smaller than 7j. Now, let's say, suppose, because what we're trying to prove is that 7k differs from n by less than 7. So let's suppose, for the sake of contradiction, that 7j differs from n by more than 7. And what does this mean about 7j? So 7j is greater than or equal to n plus 7 because it has to differ by greater than or by at least 7. So let's actually change that to at least. Because the direct opposite of less than is at least. So 7j is greater than or equal to n plus 7. And this also means that, which implies j is greater than 1, since if j is 1, it means that 7 is greater than or equal to n plus 7, which means that n is less than or equal to 0, which means that n is not a natural number. Okay, so with this, thus, let's look at a different element in that set. 7j minus 1 equals 7j minus 7, which is greater than or equal to n plus 7, because remember, 7j is greater than or equal to n plus 7 minus 7, which just equals n. So 7j minus 1 is greater than or equal to n. Now, what does that mean about 7j minus 1? This means 7j minus 1 is greater than or equal to n. So 7j minus 1 is contained within that set S that we defined above, because j minus 1 is a natural number, because j is greater than 1, and 7j minus 1 is greater than or equal to n. So 7 times j minus 1 is contained in set S. But remember from before, 7j is the smallest element in S. And since 7j minus 1 is smaller than 7j, 7j minus 1 is not in set S. So it's both in and not in set S. That's a contradiction. So thus, we have a contradiction. So there exists a natural number j such that 7j differs from n by less than 7. So as a result, we found that integer, and we've proven the original statement that you can find some natural number that such that 7 times that natural number differs from n by less than 7. So we've gone and proven the theorem. Okay, so let's block this part off, because now that we have the well-ordering axiom defined, we can now move forward into the division algorithm. Let's see if I have room. I don't think I have room down there. Let's start up here then. So now that we understand the well-ordering axiom, we can move to the division algorithm. Actually, let's use what I have down here to give examples. So to understand the division algorithm, let's briefly look at long division, which you should have learned probably in elementary school if they're still teaching that. So let's take 13 divided by 529. Well, 13 goes into 52 4 times. And 13 times 4 is 52. So then 0, and then you bring down that 9. And you see 13 goes into 9 0 times, so you have a 0 here. 0 minus, and your remainder is 9. So the things that you have here, you have 13, you have the 529, you have 40 as the answer to what 529 divided by 13 is, with remainder 9. And what this gives us is a decomposition here of 529 equals 13 times 40 plus 9, where 0 is less than or equal to 9, and is less than or equal to 13 minus 1, or 12. Now the question here is, are we able to do this with all pairs of natural numbers? And additionally, is our answer unique? Is there only one way to do this decomposition? Are there other ways? Are there other pairs of numbers other than 40 and 9 that could solve this? That's the question that we're trying to answer, and that's what we're trying to prove when we're trying to prove the division algorithm. We're trying to prove these things true. So, stated more formally, let's look at the division algorithm. So the division algorithm is this. And I'm going to write this out pretty long so that we can separate the two parts of the theorem. Let n and m be integers with n being greater than 0. Then there exist integers q, which is the quotient, and r, which is the remainder, such that m equals nq plus r, and 0 is less than or equal to r is less than or equal to n minus 1. So that's kind of what we were saying before with that decomposition. So where m would just be that 529, the 13 would be n, 40 would be that q, that quotient, and then 9 would be the remainder. Okay, so now that we have that, this is the existence clause, basically. So we want to show that this decomposition exists. And you'll see proofs like this a lot where you're trying to prove the existence of something or some sort of form of decomposition or some type of number. The next part is the uniqueness part. We want to show that there's only one way to do this. Hopefully I can spell. So for the uniqueness part of this, we'll say moreover, if q prime and r prime are any integers that satisfy m equals nq plus r, which equals nq prime plus r prime, with 0 being less than or equal to r and r prime being less than or equal to, and both of those being less than or equal to n minus 1, then q equals q prime and r equals r prime. Basically means there's only one way to solve this equation. There's not different lists of q and r that you could use to also make this decomposition. So there's only one way to do it. Okay, so to do this proof, we're going to start with existence. And in the existence proof, we're going to use the well-ordering axiom. And then we're going to go to uniqueness after that. So let's do our proof. We'll start with existence. So for our proof, we're going to let n and m both be integers with n being greater than 0. And then we're also going to let s equal m minus nx, where x is an integer and m minus nx is greater than or equal to 0. So technically this is a set of natural numbers plus 0. 0 can be included in this, But in this case, the well-ordering axiom still applies because there's a lower bound to that set. And sometimes you'll see the set of all natural numbers being defined as all numbers 1 and above and 0, and sometimes not including 0. It doesn't technically matter for this particular proof. We can still use the well-ordering axiom here. So I just wanted to say that now before I use it. But this basically defines our set of candidates for R. So like m minus nx, it's m minus n times some integer, and it gives us some remainder, basically. So these are a set of candidates for R. Now, the first thing that we want to do is show that S is a non-empty set. So when x equals negative absolute value of m, because m is an integer, absolute value is just the distance from 0, so it would be the positive version of a negative number, or if it's a positive number, it just remains that number. So the number would still be an integer. So m minus nx equals m minus n times negative absolute value of m, which means that m minus or m plus n times the absolute value of m equals this. And then since n is greater than or equal to 1, we can say that this, since the absolute value of m is positive, is m plus is greater than or equal to m plus 1 times m, absolute value of m. And all of this is greater than or equal to 0, because if m is negative, it would just be m minus m, which is 0. But if m is positive, it's m plus m, or m, it would be a positive number plus a positive number, which is 0. Which is definitely greater than 0. So if m is negative, I didn't explain that very well. If m is negative, it's the absolute value of m, which is a positive number, minus that same value but negative, which brings it to 0. And if m is positive, this would just become 2 times m, which is also greater than or equal to 0 because m is positive. So basically the point of this is that if you plug in the negative absolute value of m for x here, which is an integer, then this value here, m minus n times x, is positive, so we know that in that case, we know that m minus nx is part of the set S when x equals the negative absolute value of m. So S is non-empty. Okay, so then by the well-ordering axiom, because the well-ordering axiom applies to natural numbers and to natural numbers, including 0. Whether you include 0 or not, the well-ordering axiom applies. And this is a set of natural numbers because all greater than or equal to 0. So by the well-ordering axiom, S has some smallest element R. Okay. So by the definition of S, from above, R is greater than or equal to 0, because all elements of S are greater than or equal to 0, and R equals m minus nq for some integer q. Okay, so now we have some candidate for R, and then we know that R is greater than or equal to 0. And we know that there's this decomposition here where if you just move this nq to the other side, just added it to both sides, you'd have that equation that we're looking for, m equals nq plus r. But we only have that r is greater than or equal to 0. We don't have yet that r is less than or equal to n minus 1. So to show this, we want to find this upper bound on r. So what we're going to do is suppose, for the sake of contradiction, that r is greater than n minus 1. So, in other words, r is greater than or equal to n. Because if it's greater than n minus 1, it can't be n minus 1. It has to be n or larger. Then, we already know that 0 is less than or equal to r, but if r is greater than or equal to n, we can subtract this n from both sides, and we can see that r minus n is greater than or equal to 0, which means that m minus nq minus n is also greater than or equal to 0. And this means that m minus n times q plus 1 is also greater than or equal to 0. Now, since q plus 1 is an integer, this means that r minus n is actually in the set S. So q plus 1 is an integer. M minus n times q plus 1 is x is greater than or equal to 0. So m minus n plus q times q plus 1 is in the set S. And since that's equal to r minus n is in the set S. That's what we've shown there. So since r is the smallest element of S, r is less than or equal to r minus n. So n is less than or equal to 0. But from above, remember we defined that n is greater than 0. But n is greater than 0. So we have a contradiction. As a result, we've basically proved existence here. So hence we've shown that m equals nq plus r for some q r in the set of all integers, where 0 is less than or equal to r is less than or equal to n minus 1. So we've shown that these exist, but we haven't yet shown that they're unique. How can we show that these are unique? So let's look at uniqueness next. So to prove uniqueness, we're going to start by supposing that q prime, r, and r prime are all integers that satisfy m equals nq plus r, which also, and m also equals nq prime plus r prime, with 0 is less than or equal to r and r prime, and both are also less than or equal to n minus 1. Then we know that 0, we're going to just decompose 0 quickly, is m minus m, which also means that it's equal to nq plus r minus nq prime minus r prime. And this means that 0 equals n times q minus q prime plus r minus r prime. So we have 0 equals n times q minus q prime plus r minus r prime. So with this, what we get from here is so r minus r prime equals, so we're going to subtract from both sides, which is going to flip that those two terms around, equals n q minus q prime. So next, what we can do, I'm going to run out of space here. So, but first, let's note that r prime minus r is less than or equal to r prime, which is less than or equal to n minus 1, which is less than n. So r prime minus r is obviously going to be less than or equal to r prime, because this r is greater than or equal, both r's are greater than or equal to 0, which is, as we know, is less than or equal to n minus 1, just from the definition of r prime here, which is ultimately less than n. Additionally, we know that r prime minus r is greater than or equal to negative r, because we're taking this negative r and adding a positive term here, this r prime. And this is going to be greater than or equal to negative n minus 1, which is greater than negative n. Okay, now let's move to the top again and continue this proof. So let's just draw a line up to the top. Just to keep myself organized here a little bit. Okay, so based on this, what we have is, so we have negative n is less than r prime minus r, but we also have r prime minus r is less than n. And this implies that negative n is less than n times q minus q prime, which is less than n. Because remember, r prime minus r equals n times q minus q prime. If you remember from all the way down here, we're going to move all the way back to the bottom. Right here, we showed this. So using this inequality, let's just organize this, which implies so since n is not 0, what we have here is we can take out this n basically. Since n is not 0, we have negative 1 is less than q minus q prime is less than 1. But remember, we know that, so q and q prime are both integers. So the difference between them is also an integer. Now, what integers are strictly greater than -1, but strictly less than 1? -1 and 1 are not allowed. The only integer that satisfies this value is 0. So since q minus q prime is an integer, q minus q prime must equal 0, so q equals q prime, which shows that the q is unique in the division algorithm. Now, hence, r equals m minus nq. Now, since the q's are equal, we know that that also equals m minus nq prime, which equals r prime. So we've shown that r equals r prime. And this basically shows us, this proves uniqueness. We know that there's only one possibility for r and q. If we have two different equations that equal, or two different decompositions, the q's must be equal and the r's must be equal. So there's only one ultimate solution to this. Thus, n and q are unique. And that proves the division algorithm. We've shown that there exists these n, or sorry, not n and q, it's r and q. Thus, r and q are unique. So we've shown here that these r and q exist. There is some way to decompose this integer with the division algorithm, and that this decomposition is unique. There's only one unique remainder for any division problem. There's only one unique quotient for any use of the division algorithm. Okay, so with this, let's block this stuff off, and we can go into the final section of this video. In this section, we're going to talk about congruence and how congruence relates to the division algorithm. So let's get into that in a second once I block this off. Okay, let's hope I have enough room. I should. So finally, what we're going to do is show the connection to congruence. And I obviously forgot to switch it to division algorithm again. That's fine. I need to get better with changing these headings, I think. But it's fine. We use the well-ordering axiom in there, and yeah, I think it's okay. So the connection to congruence. So the point here is there's an important connection between the division algorithm and congruence, which we learned about in the last video. So if the remainders are the same when divided by the modulus, the numbers are congruent. That's the essential point here. That's the essential connection to congruence. So let's look at theorem 1.28. And for this theorem, we're going to let a, b, and n be integers with n being greater than 0. Then a is congruent to b mod n if and only if a and b have the same remainder. When divided by n. Okay, so for our proof, we're going to show each direction of this if and only if statement. So let's start with the proof here. We're going to let A, B, and n all be integers, with n being greater than 0. Okay, so the beginning of the proof, we're going to show this direction of the proof. So if a and b are congruent mod n, then a and b have the same remainder when divided by n. So let's start with that proof first. So for that proof, what we're going to do is suppose a is congruent to b mod n, so n divides a minus b. Then a minus b equals nx for some integer x. So by the division algorithm, we have the following. A equals nq1 plus r1 for some q1, r1 that are integers with 0 less than or equal to r1 less than or equal to n minus 1. And we also have b equals nq2 plus r2 for some q2, r2 in the set of all integers with 0 less than or equal to r2 less than or equal to n minus 1. Ooh, I have no room. Let's make this a little bit bigger so I have some room. There we go. Okay, that's great. So by the division algorithm, we have that. And because of this, thus, a minus b equals nq1 plus r1 minus nq2 plus r2, which equals nq1 plus minus q2 plus r1 minus r2. So because of this, so let's just draw this out a little bit more clearly. Hence, we have two ways of writing a minus b now. A minus b equals nx plus 0, and a minus b equals nq1 minus q2 plus r1 minus r2. Now remember, the division algorithm produces a unique combination of q and r. So what we have here is a minus b is being divided by n, and it produces a quotient of x and a remainder of 0. Here we have a minus b is divided by n. It produces a quotient of q1 minus q2 and a remainder of r1 minus r2. Now, what's important here, we don't care as much about the quotients being equal to x, but since these remainders are unique, r1 minus r2 has to be equal to 0. So by the uniqueness of the division algorithm, we know that we know that 0 equals r1 minus r2. So r1 equals r2. Now what were we trying to prove again? Let's go back to the top. A and B have the same remainder when divided by n. We're trying to show for this direction that if A and B are congruent, they have the same remainder when divided by n. So what did we do? We showed that R1 equals R2. Now, R1 is the remainder of A when divided by n. R2 is the remainder of B when divided by n. So we've shown that the remainders when divided by n between A and B, which are congruent, are the same. So we've shown that that part is true. We've shown this direction of the biconditional be true. So check. We can finish up with that, and now we can move on to the other direction. So for this direction, what we're going to do is suppose that A and B have the same remainder when divided by n. So what we see here is that A equals NQ1 plus R, and B equals NQ2 plus R for some Q1, Q2, and R all in the set of integers, where R, where 0 is less than or equal to R, is less than or equal to n minus 1, sorry. Thus, what do we have? A minus B. So now we're just going to subtract these. And what we see is that when we subtract these, we get NQ1 plus R minus NQ2 plus R. And from here, we get A minus B equals n times Q1 minus Q2 plus R minus R. So what do we have here? We have A minus B equals NQ1 minus Q2. Now Q1 minus Q2 is an integer, so that means that n divides A minus B. Thus, what do we have? We have A is congruent to B mod n, just by the definition of the modulus symbol, or by the definition of congruence mod n. And that is our proof. So we've shown both directions of this. And what this means is that the division algorithm, you can use the division algorithm to check remainders, and if two numbers have the same remainder, then they're also congruent mod n. Additionally, on the other hand, it means that if you already know that two numbers are congruent mod n, then they're going to have the same remainder when they're divided by n. It's showing here the connection between congruence and the division algorithm. We see that remainders are sort of indications or equivalent to congruence mod n. Okay, so that's everything for today. That's all that I wanted to talk about today. That's all I have for the division algorithm. It still ended up being a long video, even though it covered one topic. These math videos tend to go pretty long, but I don't know, they're nice to prepare. I enjoy preparing them and writing down the proofs, and super fun. So if you guys also enjoy this content, feel free to let me know by leaving a like and a positive comment. I always love the supportive comments. And feel free to subscribe if you want to be notified of this content and want to see more of it in the future. I got a lot of subscribers after the proof content, which really motivated me to make more of this math content. And if you really want to support, go support me on Patreon. That'll really motivate me to produce more of these videos. A few dollars is a little bit more valuable than a little subscriber. That's okay. I appreciate all my subscribers. I don't need the Patreon money, but if you feel very generous, feel free to donate. I would appreciate that a ton. And if you want to ask questions, join a community, I have a Discord link below. The community is really small, but eventually maybe we'll get big if this channel ever blows up, which who knows, may happen sometime soon, God willing. But yeah, I think that's everything that I have for today. Feel free to call me out in the comments if I did or said anything wrong. I already noticed one mistake is I always forget to put up these little what are they called, headings to stuff. So I'll probably make a note of that in the comments. I guess it's not the end of the world. It's not worth re-recording anything, but yeah, I want to thank you all for watching, and I hope to see you all in the next video. Peace.